Hello. I just want to say from my end, sharing the screen, it seems like it's kind of like repeating.
Yeah,
Is it-
I'm just on the Google Meets
that's
window.
funny.
That's why. Yeah, when I switch, you'll be able to see
Yeah, yeah.
the presentation.
Okay, yeah, perfect.
Yeah.
So hello everybody. Thank you again for participating. I think we can start now. Well, first I would like to thank you, Yiannis, for accepting to give this seminar. Uh, the title is Automatically Repairing AI Code Using Large Language Models and Bounded Model Checking. Yiannis is a PhD candidate at University of Manchester. He works with Lucas Cordeiro that helped to organize this seminar, but unfortunately he couldn't attend. Uh, uh, Ian's works with automated program repair, language models, and bounded model checking. Thank you, Yanis, for accepting again. Thank you, everybody. And just to warning again, everybody, this meeting is being recorded and transmitted via YouTube. It's a recommendation that is necessary. So you can start when you want, Yanis. Thank you.
Thank you very much. So, okay. Hello everyone. Before we begin, I would like to thank UFAM for inviting me to present, and also thank you for coming to this seminar. My name is Yiannis Charalambous, and today we'll be talking about automatically repairing AI code using large language models and bounded model checking. So the idea behind this experiment will be introduced, but first let's talk about the overview. So we will go through the introduction, then we will go through the first experiment, which was to create an AI C code data set and of unsafe and safe samples. And experiment two is running prompt engineering experiments. Experiment three is creating an iterative automated program repair framework. And finally, we will go to the limitations of this study to give like a cautionary warning. And lastly, we will go to conclusion and future work. So to begin with the introduction, we'll talk first about the team members. So first of all, basically, I would like to thank all, like Professor Lucas Cordero and Dr. Eduardo Manino. Without them, this would not have been possible. Dr. Lucas is also my supervisor, and he leads the group that we're in. He is the group head of the S3 group, which is the Systems and Software Security Research Group. He's the director of ARM Center of Excellence, focus on software model checking, automated testing, synthesis, and security. And he implemented tools to verify significant industrial programs in Java, C, C++, and CUDA. Dr. Eduardo Manino is a lecturer and member of the S3 group. His focus is on verification of testing and neural networks. His background is in theoretical machine learning and algorithmic game theory, and he worked on language models and NLP in general since 2021. He has publications at Neural PS, IJC AI, ACL, and TACAS. As for me, I graduated in 2023 with an MEng in computer science at the University of Manchester. I'm doing my first year PhD at the University of Manchester, studying automated program repair using bounded model checking and large language models. And also, I'm working on a tool that is since before my PhD, I have been working on researching this topic of the PhD, and my results are basically being put into the CSBMC AI tool. So to give a little bit of background to our group's work, we're developing and researching we're developing a bounded model tracking tool called DSBMC. It is a logic-based verification for verifying the safety and security of software systems, and it uses it finds safety errors in source code and programs by BMC, K-induction, abstract interpolation, and SMT solving. So to continue, so what is the idea behind this research? So basically, to give a little bit of background, if you try to generate code with without an oracle, so the LLM will generate unsafe code. It is important to have a code safety oracle to verify the safety of the code. And a code safety oracle basically is a program that will judge if another program works correctly. So in this case, we can combine large language models which may produce safe code, but most of the time produce unsafe code, and ESBMC, which was seen in the previous slide, to automatically repair C code. Using ESBMC as the oracle of safety and large language models as the code synthesis module. And all this equates to ESBMC AI. And here is an example on the right where there is such a problem. So here's a diagram of ESBMC AI. So first of all, we can see here on the, we give it the source code, and then we pass it to the ESBMC tool, which will then formally verify the source code. It will give you either verification successful, in which case the source code is safe, or it will give you verification failed, which means a property violation is found. So if a property violation is found, then a counterexample is generated, which is then passed to the LLM module along with the source code. And then a suggested candidate to repair the source code is found. And this leads to a cyclical, like an iterative loop style repair. So what is the motivation behind the repairing AI C code? So as society increasingly depends on artificial intelligence, the need for trust in neural networks becomes more critical. However, neural networks often exhibit vulnerabilities that can undermine this trust. In this seminar, I will present our research group's effort to enhance the reliability of neural networks embedded in C code. We utilize large language models in conjunction with bounded model checking to identify and repair these vulnerabilities effectively. So the objective here is to combine large language models and formal verification to generate efficient, robust, and secure AI code. So before we begin, I would like to also give another definition of what is AI C code. So to formally define this, we have when neural networks are transpiled into C code, the high-level neural network representation is converted into portable C code. This code can then be included into embedded systems as it's small, efficient, and portable. So tools such as Keras2C and ONNX2C are used for this purpose. So what are the research goals for this study? So the following research goals equate to each experiment because there were 3 total experiments conducted. So can we build a data set that can be used in future to train AI to repair AIC code? Additionally, are state-of-the-art verifiers like ESBMC capable of verifying the AIC code? Do good prompts positively affect the performance of LLMs in automated repair? And the third research question is there a better approach to repairing AIC code than single attempt repair? Because as you know, most tools out there and most approaches is you have the problem, you pass it once through the LLM, then you get the solution. Or you pass the problem through different tools, and then you get the, a candidate list of solutions, and then you get the best one. However, we search here for another approach. So first of all, I would like to also give a demo of my tool, the ASBMC AI tool. So if we go here, I shall begin. So here is the faulty source code. And so ESBMC AI uses bounded model checking to identify vulnerabilities. At the end, it will output a counterexample that proves that the code is unsafe. So in this case, the code is being parsed by ESBMC using the bounded model checking. These counterexamples are supported by mathematical proofs and stack trace and it gives a stack trace of the vulnerabilities to the LLMs. So in this case, we've got an explanation from the LLM, in which case it can help us identify and parse the problem that the counterexamples like gives out, because it can be quite complicated if you don't know how to parse it properly. So we call then fixed code to attempt to generate a solution. And we use a prompt template. As you can see, the solution has been generated. But basically, the way it works is we use a prompt template with the information of the source code and ESVMC output, which contains the counterexample, the error line, along with the number and type of the error. This built prompt is then passed to the LLM, which is instructed to attempt to fix the code. And the new code is once again verified with the SBMC, as mentioned previously. So as you can see, this code has successfully been fixed in the first attempt. And we can also ask questions on what changed in this solution. So to go back to the presentation now, we'll go to the first experiment, which is creating an AI C code data set. So the research goal here is, can we build a data set that can be used in the future to train AI to repair AIC code? Additionally, are state-of-the-art verifiers like ESBMC capable of verifying the AIC code? So to give a little bit of background of Neural Code Bench, it is a data set of microcontroller C code, which has a known ground truth. And it has a width of 1 to 1024 neurons, depth of 1 to 4 layers, and it contains feed-forward and recurrent neural networks, along with 8 activation functions implemented in pure C. So yes, and the methodology to generate this data set was to use Neural Code Bench as a baseline data set, obviously because we were trying to generate a lot of samples. And we have the Neural Code Bench, which we know the ground truth of. So we can then use MOL, which is a mutation testing suite, to mutate the code and generate unsafe patches. This doesn't mean that they'll all be unsafe. So we need to actually apply the patches in the base dataset to derive the new and safe or unsafe samples. And then we use ESBMC to classify, to see if they're safe and unsafe. So due to the complexity of these networks and checking for different properties of correctness for the neural networks, we're focusing on memory safety properties, as this is very exploratory. So what is MOL? So MOL is a Clang compiler level plugin based on LLVM. along with a program that runs the mutations. So Mol generates mutations of the program, so that is the compiler plugin, during compilation and injects them into the LLVM bitcode. And the enabled mutations are hidden behind conditional flags that allow them to be individually enabled. So Mol runner, the runner program in this case, runs the program multiple times with each mutation condition enabled and checks how the injection of the mutations affect the execution of the program. So each mutation can be saved into a patch file and then stored on disk. So this is an example of running Mol. So we compile each sample using Clang and the LLVM compiler plugin. We use Mol runner to generate the patches, and then we save the patches using a file. We save the patches to a file and then apply them using the GNU patch program. And here's an example of one of these patches, in which case it changed this line. So instead of having the start of the loop be j equals ndim -1, we have it j equals ndim +1, which we will see if we don't know if this will cause a memory vulnerability, which is why we need to use ESBMC to check. So in this case, the results of the data set can be used to train an LLM in the future with the output from ESBMC and the verifier. So code classified as unsafe can be used as the faulty code in the X train of the AI, which is being trained, and then the code classified as safe can be used as the safe code in the X train and Y train of the AI in this case, because we have a list of correct and safe and unsafe samples, which we can give to the which we can use as training data. And then, of course, we need to have the safe code, because the whole point of training the AI is to generate the safe code. So here are the results of the data set. So as you can see, a lot of the samples that were classified, that they were unknown in the hop field and reinforcement categories. However, there were a lot of safe and unsafe successfully verified samples as well. So the timeout set on ESBMC was too small, even though it was set to 300 seconds. However, some samples were completed around the 200-second mark still. So here, the lessons learned were, even when given a large amount of time, ESBMC had difficulty verifying the memory safety of a large portion of base and derived samples. So this isn't just an issue with ESBMC. It's worth noting that it's an ongoing research issue, and it's because of the complexity of the code of these AI systems. So this is an ongoing research by our group to push the state of the art and improve ESBMC. And the verifier had the least amount of success in the hop field nets, which are recurrent neural networks, followed by reinforcement learning category, which are feed-forward neural networks. The verification time of hop field nets were larger than polyapprox and reached probability density. So to go into the next experiment now, which was running prompt engineering experiments. So the goal here, the research goal of this experiment, was, do good prompts positively affect the performance of large language models in automated program repair of AIC code? So to give a little bit of background, what is prompt engineering? So the performance of generative language models strongly depends on their input prompt. So in the past few years, researchers have learned strategies to optimize the input prompt, and strategies can range from simple instructions to the LLM, such as fix this code, here's the source code, to personification strategies such as role play. So we aim at comparing a few prompt strategies to find out which one is truly the best in this field, which is repairing AIC code. So Here we have the types of prompts that we have decided to create. We created 3 types of prompts: simple, persona, and I don't show here, but we also have the old ESBMC AI prompt, which was the original prompt, which we wanted to test to see how good it was, which turns out it wasn't good, so I have omitted it from the presentation. However, for the persona prompts, we have additionally the following roles assigned to them, because persona is essentially role play. You assign a role to the LLM, and you basically instruct it to do the task as that role. So in this case, we assigned 3 categories, which is control roles, which is meant to establish a baseline measure. So these were the smartest dog, the smartest human in the universe, and dog. So these are meant to be very far apart from anything else. And the reason for this is due to the fact that we wanted to not perform good at all. We want it to be a control role. So then we have a humanoid expert. So here we're trying to get as good performance as possible. So we have programmer with 1 million years of experience and senior software engineer. Then we also have robot tool, which is an automated code repair tool, and artificial intelligence that specializes in repairing C code. So we have a humanoid and an object sort of category as well, because the idea is that when you speak to LLMs such as ChatGPT, they have an idea of a self. This is not because they're alive or anything, but it's because their training data specifies them as such. So when you're training ChatGPT, you're going to say, oh, you are an LLM, you are this, you are that. So we're trying to see here in this case, which role would fit best in this sort of use case. So additionally to the prompt template, to the prompts and to the types of prompts, we have the prompt groupings. So for each role here, we created 6 different types of prompts, which are grouped into 3 groups. So we have two prompts per group. So in this case, we have each group has so each group, one of the groups is no ESBMC output. So in this case, we're just passing the source code. Then we have ESBMC output after the source code and ESBMC output before the source code. So yeah, and the reason we have 2 prompt templates created for each group is that one of the prompt templates is shorter and simpler than the other one. So no ESBMC output will have a short one and a long one, so will the others. And the idea for showing the ESBMC output before and after the source code is we want to see, so the way that ESBMC, the way that the ChatGPT encodes information is using the attention mechanism. And we want to see if the ESBMC output matters, if like at what point where we include the ESBMC output, does it help generate correct repairs? So here's an example of a simple prompt. So each example here follows the following classification as described in the last slide. No ESBMC output, ESBMC output after the source code, and ESBMC output before the source code. And yeah, each one has a set of a long and a short template created. And this was done to experiment with if giving more detailed and specific instructions to the LLM would increase performance, as this was another vector we wanted to test. So, and these here curly braces specify where the source code and the ESBMC output would be included. So again, here we have the persona roles, in which case we assign a role as well. So we need to show the LLM the vulnerable code to be repaired. The amount of text that we can show the LLM is very limited. In the case of ChatGPT, it is stuck to 16,000 tokens for GPT 3.5 Turbo. So we have to limit the source code and the SBMC output, and we can do so by formatting them. So we have come up with two possible solutions. In this case, we have contextual experiments and single line experiments. So in the contextual experiments, the prompt needs to expand to take as much of the context length of the LLM as possible to fit as much code as possible in the available space. We cut the largest window of code around the reported vulnerability. We also select a window that contains around 90% lines of code before the vulnerability and 10% after. So you can imagine the vulnerability, and then 90% of the context is filled with code before it, 10% after. We also reserve a space for the SBMC output as well, which we will talk about soon. So for single line experiments, the idea is that for many memory safety vulnerabilities, such as array out of bounds, it is likely that modifying the very same line of code that triggered the verifier is sufficient to repair it. And in this case, mul only mutates one line of code. So we want to see how effective the LLM is when it is given almost like the exact location of the error along with what the error is. So for this reason, we run a full set of experiments showing only the one line of code to the large language model. And the ESBMC output included remains unchanged. So now we'll talk how we format the ESBMC output. So we have two types of formatting. The smallest option is verifier output, which as you can see here, just contains the file name, the line number where the error is, the column, the name of the function, the error, and also and the type of error, and then the exact error. And then we have the largest option, which is the counterexample, in which case it prints the entire state and the entire state of the stack trace which can lead the LLM to the error. So you can imagine it as if you follow it along, it will lead you to the exact state where if you were to reach would cause the violated property to occur. So here we want to experiment with what parts of the ESBMC output the LLM is trained on, if any. When prompting ChatGPT if it knows about ESBMC, it answers that it does. So, so is it trained on any output? But the main research point here is to observe if LLMs can understand the verifier output and also reason about it. So here's the list of the amount of prompts that we ran. In total, we ran around 144 prompts on each sample that we ran on. So now we're going to go through the empirical comparison of our results, and we will also discuss any research implications that the results have. So first of all, the repair performance of the LLMs is measured on 4 metrics of increasing difficulty. We have syntax, relevance, compilation, and verification. In the case of syntax, we ask, do the repair patches contain C code, or does it just, output anything else, which would be totally wrong? For relevance, we ask, do the repair patches match the input source code? And in the case of contextual, will it output anything that is matching the original code, because it still needs to modify a single line? For compilation, we ask, do the repair patches compile? And verification, do the repair patches solve the memory safety vulnerability? So verification is the holy grail of what we're trying to achieve, but we want to see how far the LLM actually got before it failed. So for the syntax of the LLM matching results, we have to confirm the LLM is producing actual C code. The results show higher scores for contextual prompts when comparing to single line. We can see that the persona prompts yield a higher percentage of C-like LLM outputs for contextual strategy and other prompts. This could be also a limitation to the classifier used to automatically detect the results. So this is a warning, like we use the Visual Studio code classifier, which is used in industry. However, we still gave it one line at the end of the day. So these results should be definitely taken with a grain of salt. However, these should not, because they are many more lines of code. However, the main observation in this slide is that the graph to the right, so this one right here, shows that the verifier output to the prompt appears to make things worse for the contextual strategy, but better for the single lines of code. So this could imply that filling up the context space of the LLM with information could see a drop in performance. So the LLM needs to be carefully, so the information needs to be carefully picked, possibly. So now we move on to point number 2, which is relevance of the LLM patches results. So here we expect a successful patch to copy most of the input verbatim, except for a small difference, which is the line of code that it is changed. We measure how many characters the input and output code have in common. So for contextual strategy, this has a low match, as the LLM sometimes reports only a few lines of code around the bug instead of copying the entire code. This implies, once more, that the LLM may have trouble encoding the entire code into its attention, and put it simply, recalling the entire code. Or it could also mean that the LLM may be trying to unsuccessfully simplify the code, because it may see a better way in specifying that code. However, in this case, it's probably wrong. I mean, yeah. So the anomaly for single and simple prompts also, like here, as you can see, may be due to temporary changes in ChatGPT backend that are out of our control. We couldn't identify why this results here occurred. So also, another observation is adding feedback from ESBMC to our prompt seems to lower the performance of the LLM as specified before. So in future experiments, we definitely need to apply some formatting. So now we move to compiling the repaired code results. A common observation throughout these measurements is that with the large code supplied to the AI, it is unable to fix the code. However, instructing the LLM to repair a single line is much more successful. The issue seems to be with the volume of information it needs to remember. Because keep in mind that since this is an entire AI code, including like all the weights of the AI, this could this is a lot of information. Like it fills the entire context space of the LLM. So a large majority of the runs did not produce any code that compiles. So now we move on to verifying the code, which is actually it contains a very interesting discovery. In fact, like this is like I had no idea this would be the result. So we have here all the repair patches that were generated using the contextual strategy display an interesting property. If the code compiles, then it is also successfully verified. So if you look at the previous graph and you compare it, it matches, like the contextual row matches exactly with the compilation experiments. So this means that if it compiled, then it was verified successfully. So one-line repair patches yield more successful repairs overall still. And the persona prompt techniques, no matter the specific role chosen, are very clearly the best. So to summarize, the best prompt discovered was managed to get 18% successful repairs of the AIC code, which is very impressive considering that this was out of distribution data. And showing a single line of code is better than showing the code contextually. And the descriptive persona prompts work the best. And the best role for the persona prompt was automated code repair tool. Showing the source code after the verifier output is also better. And providing raw feedback from a verifier makes the performance slightly worse. And this is possibly due to out of distribution, again, like the output from verifiers. So here we have also the best prompt template that we have. Whoops, best prompt template. And the contextual scheme of filling the LLM context with AIC code causes a different performance. And I believe this is too much information to be encoded in the attention mechanism, or it's because it is not trained on the input given to it, and it can't generalize well enough to successfully repair the code. Here, further research is necessary, as it could uncover whether these tools are good for generalizing and coming up with new information, or if they are simply very simple recall machines. So now we move to the third experiment, which is creating an iterative APR, or automated program repair framework. So here the research goal is there a better approach to repairing AIC code than a single attempt to repair? So allocating multiple attempts to repair the sample may increase the successful samples repaired. The LLM must successfully patch the source code within the allocated attempts. And if the total attempts exceeded in the limit, in this case 5, then the verification fails. So for prompt settings, we use the best prompt template from the previously seen prompts. So sorry, we use the best prompt template from the previously seen prompt engineering experiments. We add further instructions to the best prompts to produce 2 additional prompt templates with the following features. So we grabbed the best prompt template that we got from the previous experiment, and we created an even more specific one, which is to explicitly instruct to use the verifier output to fix the bug, instruct the LLM to only repair a single line of code, and to minimize the size of the changes. And the idea was to see if we can push this slightly further now that we had a pretty good prompt in our hands. And this leaves us with 4 prompt templates total for this set of experiments. So for the source code prompt settings, we chose to go with single line source code formatting only, as the contextual source code formatting is not compatible with iterations. This is because the contextual style source code fills the context space in the single attempt fully. For the ASVMC output, we chose to use validated property, as it would guarantee fitting in the input space of the LLM. And this is due to the cyclical nature of the iterative experiments. The CE output, which is the counterexample output type, becomes incompatible as it is very large. Validated property shows only the statement where the property is validated, the type of error, and the location where the error occurs, so it fits very nicely. So another prompt setting that we had to consider in this case, since we're iterating, how shall we represent the history, if at all? So in this case, the 3 methods that we came up with representing the current and previous messages are denoted as forward history, which, as you can see here, we show the history of the changes in the code and verify output starting from the oldest. Then so the first message, response, then we repeat until we get to the latest message. We go to reverse history, which shows the history of the changes in the code and verify output starting from the latest, in which case we go the latest. We've got basically forward history and reverse. So the forward message, so the first message is last, the response is second last, and then the latest message is shown first to the LLM. Then we go latest state only, which shows only the last state of the code and the verifier output. So in this case, we're basically trying again and again and seeing if it can get lucky. So we have here the following temperatures. We run the experiment with these 5 set of 5 temperatures. Basically, the aim is to determine which temperature constitutes the best performance for AIC code automated program repair. And as for the sample size, for comparison reasons, we use the same code samples that we chose for the previous experiments, where we found the optimal prompt. The research reason for this was to determine if at specific temperatures the APR process is more effective. So now we move on to the experimentation results. So in this case, we have the first research question, which is, do large language models combined with formal verification increase automated program repair performance of AIC code when given multiple attempts to do so? In this case, forward history is much more successful when dealing with iterative repair. This is because the LLM can be guided to repairing the issue through its previous messages. And showing the history does improve the performance, basically. So there is a sharp drop in successfully repairing a sample after 1 to 2 retries. Giving the LLM multiple attempts at fixing the code increases the automated repair performance. And now we move to research question number 2, which is, does showing the history of patches to the LLM improve the performance of iterative automated program repair? And as you can see, showing the history does in fact improve the performance. This is because the LLM has access to the original state of the code, along with a series of feedback from the verifier. This could help in determining the actual fault rather than veering off the correct answer. Because we have the original state, which may or may not have one problem. And then if we keep trying to repair it and we only use the latest state, we will probably there's a possibility that the LLM could completely generate irrelevant code, in which case, if the verifier says this is completely wrong, it doesn't actually know what the beginning of the code was, like the initial state. So forward history has the highest percentage of successfully repaired samples for all the prompts. Latest state only has scored second for all the prompts. Now we move to the third research question, which is, what is the optimal way to show the history to the LLM? This is forward history, followed by latest state only, then reverse history. So the best way to show the prompt is forward history, and as it scores higher than latest state only and reverse history combined. Finally, we reach out the final research question, which is, what is the optimal temperature to conduct automated program repair of the AI C code? And in this case, we have a forward history, which is the lowest temperature is better. The optimal is 0.0. So as you can see, forward history right here, it kind of drops as we go higher and higher, as it starts generating more creative output, let's say. Reverse history and latest state only did not perform as well as forward history. Forward history is the best type of history as it scores higher in every temperature. And finally, what is the best prompt that we found? We found that in this case, the original prompts, which is 9 and 11, that's what we enumerated them as, at temperature 0 for forward history was the best one. So these were the prompts that were found in the prompt engineering experiments. So it turns out, as we typed a more specific prompt, the performance actually dropped. So the best temperature is 0.0. The best number of retries is 2. The best type of history is forward history. The best performance we managed to achieve is 25%. And our final verdict for these experiments is that iterative automated program repair is better than single attempt automated program repair. So before I end to the conclusion, I would like to also give a warning to the limitations of this study. So these experiments were conducted using GPT 3.5 Turbo. The model is closed source and could be updated at any time. Each model has undocumented updates constantly. Newer models could be trained with the report of the experiments after it was published online, and also trained on the repositories containing the experimental files. Rerunning the experiments at a different point in time may yield different results. It's important in future research endeavors to use open source, locally accessible models in order to easily reproduce the experiments. So I'd like to conclude with thanking everyone for watching the seminar. It was my very first seminar, so I hope you all enjoyed it. Here's a recap of what we talked about. We created a large memory safety vulnerability data set that can be used to train LLMs to repair AIC code. We used prompt engineering techniques to find the best prompt for AIC code repair. And we expanded ESBMC AI to create an iterative AIC code APR solution. And what's next for the group? We'd like to keep experimenting with large language models, run bigger, more generalized experiments with open source models, and fine tune also large language models. So For ESBMC AI, I would like to also augment formal verification with test suites. So in this case, ESBMC works in conjunction with tools such as test suites to ensure that the code also runs with the required logic. I am also putting an effort to switch from using ChatGPT to open source local models because, as you can see here, we really need to. So thank you, everyone. This is the end.
Thank you, Yiannis. Thank you for the nice talk. Now let's open to the discussions. Is there some questions to Yiannis here? The people on YouTube can also write if you want. If someone wants to ask something, please raise their hands.
I'll open the chat.
Well, I have a question.
Yes.
Two questions indeed. First is about the scalability of the results that you showed here. How can you talk a bit about the scalability? What do you think about the application to, for example, for a code with a lot of thousands of lines, for example? What do you think?
So in terms of general code, I would say it is more scalable because the LLMs are, as you know, trained on a lot of code. And I would say that the majority of it is just normal C code on GitHub. We know that GitHub also uses like private code to also train the models, which is an issue. In terms of AIC code, the point of these experiments was very exploratory, as it was never, to our knowledge, done before in this manner. And that's why also we were focusing on memory safety vulnerabilities. In terms of scalability, I would say that the scale of these codes was actually already huge, as it completely it was. So if the context length of ChatGPT 3 is 16,000 tokens. But if we were to load the entire source code without, let's say, using the contextual experiments formatting scheme, it would actually fill it like 10 times over. It would reach like 80,000 tokens. Like this is how big these AI, like the AI code is, because it contains the entire weight of the AI as well. And while these AI systems aren't big in themselves, like we saw that the width was, if I remember correctly, was 1,024, and the depth was 512, if I recall correctly. They are out of distribution, so we wanted to go with an exploratory mindset. In the future, we will possibly
Hello, it's frozen here. I don't know if only it's me. Can you hear me, guys?
Yes, Yuri. I think Yiannis is frozen.
Okay. Let's wait a bit. Hello, Jens. I think he had some connection problem. Meanwhile, if someone else wants to ask a question, you may raise their hands. Hello, Yiannis. I think you had.
Yeah, I think my connection disconnected for some reason. So just can I repeat my answer, please?
Yeah, I think you more or less
Okay.
answered.
Okay, I don't know at what point I dropped, so okay, if you understood, then that's
Yeah,
good.
yeah, I could understand. Thank you.
Okay, okay.
I would like also to ask something else, because in this case you are using the model from ChatGPT.
Yes, that's correct.
That of course he's for large language, but it's not focused on the problem and the kind of problem that you have applied. Do you think that should have some advantage in training a specific LLM uh, algorithm, thinking about uh, the verification scenarios, verification contexts? Do you think that is it possible, and do you think there is an advantage on this kind of approach instead of using the GPT one?
So you mean using a specially designed tool rather than
Yeah,
using a
yeah.
large language
Design
model?
your tool instead.
So there could be an advantage. I mean, for sure, if we were to design our own tool, it would also verify the code in itself. That's why we're, in this case, relying on ESBMC to produce to be the oracle.
Yes.
So, but the complexity and the different ways that these models can be implemented would be definitely challenging for hardware, because if we were to verify the models using tools and then repair them as well, it would be too much currently for basic for hardware. Because if you look at all of the state-of-the-art verifiers now
Mhm.
have difficulty with verifying most of the AI code. So making a tool that also repairs it would also would the main challenge would be basically would be the verification aspect first.
Okay. Okay.
So large language models are sort of like a shortcut, since if you train them, then if they're trained well enough, they can generalize to the data set, which is
Mhm.
a convenient.
Okay. I see. Is there some other question in the group?
Yes, I have one.
Please go
Uh,
ahead, Gustav.
Hello, my name is Gustavo. I recently completed my PhD at UFA in the PPGA program. I would like to congratulate you, Yiannis, for your presentation and your research as well. I have
Thank
just
you.
one question. Uh, Based on the best prompt templates you present, I assume you just use one agent to repair the code. It's right?
So by agent, you mean like, yeah, I used one, like it was the same large language model. It was ChatGPT 3.5.
Okay. Have you considered using a flow of agents instead of using just one, using like libraries like LangGraph or other
Yeah.
libraries like that?
So this is something I do plan on doing, as it does interest me. I use, just so you know, like ESBMCAI uses LangChain in the as a library, so it would be pretty, I guess, simple to implement this. However, uh, as this was exploratory experiments, we wanted to basically start off simple with like, what can one do? And then possibly in the future, what happens if we start expanding, scaling up with more agents, using additional tools, like, can we do more? But currently, we only focused on the very basics.
Yes, I believe write and fix code, it's very challenging tasks for a large language model, and I think it would be very good using multiple agents and break
Yeah,
very complex process into
I agree.
smaller ones.
Yeah, I agree. And also another challenge that we did not really that we didn't face due to the exploratory nature of this is so let's say there's a problem with like the, I guess, correctness of the AI. So what if a weight is off? Like the large language model probably wouldn't be able to correct the weights. So this is something that we did not in fact measure. We were just focusing on safety properties, in which case, let's say there's a vulnerability in the tools that are used to create the code. We would be able to then just formally verify that the actual code of the AI is correct.
Great, thank you.
Thank you.
Somebody else?
Yes, hello. Philippos Mentirosos here. I was a previous PhD in the University of Manchester.
Hello.
Yeah, we've been working a little bit with LLMs. Now, I think it would be quite interesting, like looking at Gemini as well from
Yeah.
Google, because like a super long context. I think the Flash has 1 million. The Pro has like I think 2 million context. Because it's interesting with this like very long context how it can adopt right into code.
Yeah, I agree.
Yeah, is it like really something that can work here or not?
We would have considered Gemini actually, but when we ran these experiments was that it was, I think, before Gemini like it came out. It was back when if I recall correctly, it was called BART. It was back when BART was a thing. So ChatGPT was way better than Gemini, but now there's the gap is closing between all the big corporate LLMs.
Yes, indeed. Yeah.
Yeah.
And another thing I would like to, I think that I see myself maybe as a possible future work, if I may, because you mentioned that you have some code which is safe, some code which is has some errors. I think would be like, I don't know if you have looked already, some like maybe fine tuning with kind of like contrastive learning. I guess like if you have like one code that works, one code that doesn't work, and then I guess fine-tuning LLM in that sense. I think maybe
Contrasting learning.
contrastive learning. Yeah.
Contrastive.
Yes.
Okay,
Yes.
I have not looked into that yet, but it will be very nice to read about it.
Yes.
Thank you for telling me.
Yeah. No worries. Yeah. Yeah. Because I've seen examples where I think in one sense they have like a right example, a wrong example. You get the idea, and then a fine-tuning on this, and I may have some interesting results. Yeah.
Yeah, like in the meantime, we have the data set. Like we didn't really plan like when we're gonna use it, but we have it, and for sure in the future, as you know, verifiers like ESBMC get better at verifying large large AIs. I mean, large C code, which forms these AI systems. We'll probably get more and more results, like less unknowns, as you saw the graph. Yeah.
Yeah, so thank you again for the presentation, and all the best.
Thank you. It was my pleasure.
Somebody else? No, so I would like to thank you again, Yiannis, for the nice talk. It was very good. Thank you, everybody, for attending. And I think we are in the time now. So the seminar will be available in the channel of the controls. Okay, for if someone wants to see again and to share, go ahead. Thank you.
Thank you, everyone, for spending time to watch me. I really appreciate it.
Thank you. Jan, can you stay just a little bit?
Yes, of course.
Okay.
Thank you. Bye, everyone.